The PIP-II accelerator will be the new heart of Fermilab's accelerator complex. The proton beam from this new 800 MeV superconducting linear accelerator will power a broad range of particle physics experiments for decades to come. PIP-II will enable the most intense, high-energy neutrino beam for the laboratory's flagship experiment, the Long Baseline Neutrino Facility and Deep Underground Neutrino Experiment. Key designs and technologies for PIP-II are being tested at a facility called PIP-II-IT, the PIP-II injector test. This test bed for the first 30 meters of the 240-meter-long PIP-II accelerator includes the room temperature accelerating section, the warm front end, and the first two of PIP-II's 23 cryomodules, the half-wave resonator cryomodule and a single-spoke resonator cryomodule. This fully integrated machine will be operated with beam up to an energy of roughly 25 MeV, validating component designs and demonstrating performance of the integrated system. The PIP-II-IT accelerator starts with the warm front end. The ion source creates H- ions, which are extracted to form a DC beam with an energy of 30 keV. The beam is then propagated through the low-energy beam transport, or LEBT, to the radio frequency quadrupole, or RFQ. In the LEBT, there is an electrostatic chopper that forms a macro-pulse beam structure, nominally 0.55 milliseconds at 20 Hz, from the continuous beam coming out of the ion source. This chopper is also the main beam inhibiting device for the LINAC machine protection system, or MPS. The RFQ accelerates and bunches the beam. At its exit, the beam is composed of 162.5 MHz bunches at 2.1 MeV. The last section of the warm front end is the medium energy beam transport, or MEBT. This 10-meter-long beam line prepares the beam for injection into the first superconducting radio frequency cryomodule, the half-wave resonator. The core function of the MEBT is to finalize the beam's time structure. The MEBT houses a cutting-edge chopping system that allows bunch-by-bunch chopping. In other words, any or all of the bunches that exit the RFQ may be deflected onto a high-power beam absorber or may pass unimpeded for further acceleration.
The half-wave resonator cryomodule, or HWR, is the first superconducting accelerator component in the PIP-II LINAC. It will accelerate ions from 2.1 MeV to 10 MeV. It contains 8 superconducting accelerating cavities and 8 superconducting solenoids for beam focusing, and was designed and built by Argonne National Lab. The cryomodule was carefully transported to the Fermilab in fall of 2019. It has now been installed here in the PIP-II-IT facility and recently underwent powered acceptance testing at 2 Kelvin, or 456 degrees below zero Fahrenheit. The HWR cryomodule will now be used as part of the beam studies component of the PIP-II-IT program, before later being installed in the PIP-II LINAC. The next cryomodule, named SSR-1, contains 8 single-spoke resonator superconducting cavities and 4 superconducting solenoids. This cryomodule was designed and built at Fermilab and contains several innovative features. For example, the strongback structure, which supports the cavities and solenoids and maintains their precise alignment. Engineering tests performed at PIP-II-IT will validate these design features and inform the final design process for all PIP-II cryomodules. This cryomodule has been cooled to its operating temperature of 2 Kelvin also, and as of September 2020, RF testing of the cavities and magnets is underway. Once qualified, this cryomodule will be used to accelerate beam in PIP-II-IT from 10 MeV up to 25 MeV.
After exiting the SSR-1 cryomodule, it enters a beam instrumentation section called the High Energy Beam Transport Line, or HEBT. The HEBT beam line is used for commissioning and characterization of the H- beam out of the cryomodules. This includes the measurements of beam position and phase, beam current, beam size, and beam energy. PIP-II is the first major accelerator project in the U.S. with substantial international contributions to the design and fabrication of components. One of the early international contributions is the design and construction of radio frequency, or RF, power amplifiers used to drive the superconducting cavities that accelerate the ions. Other places where one may find amplifiers at these power levels is in TV broadcast stations or radar stations. But instead of broadcasting the signal to the air, we are focusing the power into the small volume of the cavity to produce a large voltage for acceleration. The amplifiers used to accelerate the beam through the SSR-1 cryomodule cavities are provided by the Indian government, designed by the scientists and engineers from the Bhabha Atomic Research Center in Mumbai, and constructed by the Electronics Corporation of India. The low-level RF system is responsible for controlling the radio frequency field inside the accelerating radio frequency cavities to the high accuracy needed to accelerate the H- beam precisely in each cavity in the string. Timing must be controlled to less than the time it takes light to travel the width of a human hair. To do this, it must keep the cavities on the correct resonance frequency, drive the solid-state RF amplifiers, and protect the whole system from possible damage from the high energy present in the system. It also provides a great deal of diagnostic information back to the accelerator operators needed to properly tune the machine.
As an integrated system, PIP-II serves as a testbed for PIP-II front-end and critical systems to reduce technical risks. Key technology demonstrations include operation of the MEBT chopping system and arbitrary bunch pattern generation, vacuum segregation between the MEBT absorber and the HWR cryomodule via differential pumping, beam transverse profile measurements with a laser profilometer, low-level RF control of SSR-1 cavities, and several others. As we accelerate the H- beam in PIP-II to 25 MeV, we will verify performance of several of these critical systems with beam. We will also test several system prototypes provided by in-kind partners, for example, warm unit quadrupole magnets and an SSR-1 cavity provided by India. PIP-II will be used to measure beam parameters and validate beam dynamics computer models used for the simulation, optimization, and operation of the PIP-II LINAC, including artificial intelligence and machine learning algorithms. Finally, we plan to check PIP-II performance under operational regimes, simulating and exceeding PIP-II performance.